Hi, in this video we're going to go through the questions required for homework 4, inference about a single proportion. Let's begin with the first problem. It is about a survey that was done of Kansas residents, people living in the state of Kansas in the United States. There were 600 that were surveyed, and 56%, or p-hat of 0.56, of them were planning to set off fireworks on the next July 4th. In part A of this problem, number 1, part A, it says produce a 95% confidence interval for P, and I'm not explicit here, but I'm expecting that you would use the normal theory confidence bounds approach, and you can use the p-hat that I've constructed here, 336 out of 500. The standard error for the confidence interval formula is the square root of p-hat times 1 minus p-hat all over 600, and that value is computed for you in the code block right here. You can use that in your formula and your computation. The entire plus or minus part of the confidence interval formula is right here, called margin error, and that's printed out. You could use that. And you could use these pieces and construct the rest of the formula yourself to come up with the lower and upper bounds for the confidence interval for P. The other thing you could do would be to go inside the code block and take off the hashtag comment character on this prop.test command, and this prop test command would produce the lower and upper boundaries for the confidence interval directly. So I'm assuming you could either use the command, or you could construct the confidence interval either by making commands in a code block or constructing it by hand with your calculator, and that would give you the confidence interval for part A. Part B, it says determine the margin of error, and that would require you to realize that the plus or minus part of the confidence interval is already computed for you right here. You just need to repeat and type in this value in the answer for the margin of error. That would be the decimal answer. The percentage points interpretation is found by just moving the decimal place 2 places to the right on the margin of error that is provided. In part C, you're supposed to use the margin of error sample size formula that's given near the end of the notes. You are told to use a margin of error of 2 percentage points, which means that M is 0.02, a 95% confidence interval, which means the multiplier would be 1.96, and you should be able to solve the equation for the sample size that you need. Please consult the notes for that, and please remember that you have to express sample size as a whole number, not as a decimal. As a decimal fractional number. It needs to be a whole number. You can't take part of an observation. You need to take a whole observation. In part D, I ask you to do a z-test, a normal theory test of significance about whether the population proportion is different from a half. And I've given you some of the parts of the computation. Here is the denominator of the z-statistic, and I've given you that. Here is the z-statistic itself, 2.94. Here is the prop.test command if you want to get the p-value directly from that computer command. And so to give your answer, I've already provided the hypotheses and the test statistic. It would be up to you to use the p-value either here from the command or look up the p-value appropriately in table A, remembering that the p-value needs to be from a two-sided test because this alternative hypothesis is two-sided. So that would be an important consideration. And then the main thing I'm looking for here is the conclusion, that you use the conclusion language as we've been discussing in class. Moving on to problem 2. First part about the rhesus monkeys is talking about what are the observational units. Well, the observational units are the monkeys. The variable that's being studied is a yes or no variable. In each case, the monkey either gets the box towards the box that's gestured towards, or it does not. So it's like a yes or no answer, and that is of course one of these kinds of variables, either a quantitative or a category variable, please indicate which. In question 2b, I wanted you to explore the data, and that's really quite simple when all we're studying is a fraction. I think the data here is 30 monkeys out of 40, so it's a p-hat of like 3/4, I believe, is what you need to do for question 2b. For question 2c, we are going to simulate what box behavior should be like if the monkeys were just choosing the gestured box at random. And that is being done here through the R/binom command. Right here in this line, I'm simulating 1,000 experiments, each with 40 trials, and the monkeys are choosing the gestured box with probability 1/2. And in this particular instance, it looks like the simulation, what we're doing in this next line is just counting up the number of simulations where the monkeys picked more than 30 or more boxes, gestured boxes. And this does not happen very often. It looks like it happened one time out of the 1,000 simulations. And so the strength of the evidence is 1 in 1,000, and you should make a comment about that, and that means that it is very unlikely that the monkeys are, it's very unlikely to ever observe 30 gestured boxes out of 40 for monkeys that are just guessing. And so make a comment about what this says about monkeys guessing at the gestured boxes. So an additional sentence onto the strength is needed. In question 2d, we're going to perform the normal theory z-test, and I've given you the computations that you're going to need to use if you want to do this. I'm suggesting here, because my alternative hypothesis in this command is a greater than, I guess I'm assuming you're going to do a greater than alternative hypothesis for this. I'd suggest that. So please fill in the hypotheses the best you can using descriptive words in place of the symbols. If you really want to learn how to do the symbols, you can ask me or take a look in the Markdown file earlier where we did that. Please use the p-value either given from the prop.test command or from looking up 3.16 in Table A appropriately for a one-sided test, and give the full conclusion like I've taught you in class. In question 2e, you need to make a confidence interval for the parameter p, 95% confidence interval, because I've done some of the computations for you here using 1.96. The value that comes out of this code block is the value for the lower boundary, and I've also produced the upper boundary for you. You should make sure that you get those values yourself by doing the computation yourself. Give the confidence interval range right here, answering question 2e. In 2f, I am asking you about the validity conditions for this study. And in this case, there is a set of validity conditions in the notes for doing a normal theory hypothesis test, and there is a separate but related set of conditions for doing a confidence interval. Please consult the notes for doing that. Remember that the conditions for a hypothesis test are given in the notes on a slide like this one, where the number of successes expected, n times the null hypothesis p naught, has to be bigger than 10, greater than or equal to 10, and the expected number of non-events, or the expected number of failures, n times 1 minus p naught, also has to be bigger than or equal to 10. And the conditions for a normal theory confidence interval are that the observed number of events have to be greater than or equal to 10, and the observed number of non-events also has to be greater than or equal to 10. So therefore, make sure that those conditions are met for this study. Doing a test, do those conditions, and for an interval, do those conditions. In problem 3, we resume the red-blue uniform color study, but only considering boxing matches. And in this case, what we're going to do in 3A is simulate 1,000 experiments of 272 trials, each with an equal probability of winning the red uniform or the blue uniform. And from those simulated trials where red and blue win equally likely, we're going to add up the number of simulations where the number of victories for red is 150 or greater. Remember that in the problem, red won 150 times. So if we want to find the fraction of simulations that are more extreme than 150, that's what's being measured right here, where we find the number of simulated trials that are bigger than 150. But this also says we need to consider the number of matches won by the red fighter, the red boxer, to be 122 or lower. And the reason we are worried about 122 or lower is because this is the same distance below the expected number under randomness as 150 is above the expected number for randomness. And so randomness is half of what we expect for a 50-50 system, is half of 272 being observed. And that halfway point is 136. And so 150 is the same distance above 136 as 122 is below 136. And so this expression right here measures the fraction of simulations that are as extreme or more extreme than 150 wins. Turns out that that fraction is about 10%, 0.1. And so put that in right here for your p-value, and then for a p-value of 0.1, make your conclusion about how you feel about this p-hat data result compared to what you'd expect from just randomly winning the match, red or blue. That would be the simulation test result. Then in 3B, please use the normal theory z-test. I've given you the computations that you need right here. You're given a p-value from the R computer command if you need that. You'll notice that's a very similar p-value to what you get from randomization. And so in the test conclusion area in 3B, please put in, the null hypothesis. The alternative is already put in. The value of z is in here. Make sure you you put in that and leave that value of z, put in the p-value, and do your conclusion. In problem 3C, we make a confidence interval, and the computations that you need for the lower and the upper boundary are given right here. And then what you're supposed to do with it is use the interval to discuss whether a red or blue uniform color, whether there's evidence that red or blue win more frequently than by random chance alone. And since we're measuring the fraction of winning with the red uniform, you should declare that red uniforms seem to have an advantage, a clear advantage over randomness if this confidence interval would be entirely above a half. That's what you'd say. If this confidence interval would be entirely below a half, you would say, well, there's very clear evidence that red wins less often than you'd expect by chance, which is a half. If the confidence interval contains a half as one of the values, then you would probably write something like, there's not enough evidence to say that red uniforms win differently than you would expect by chance. Hopefully this will help you do your homework. As always, let me know if you have questions.